So the goal for today is to tell you about meta-algorithmic result. So it's like you can give a class of algorithms solving also like a class of problems. And the main focus of the exposition will be on the generation of large primes, but I will discuss how the techniques generalize to this more general setting. And so most of the talk is going to be about an algorithmic result, but at some point I'll mention the connection to Kolmogorov complexity. Okay, so just to recall, so prime number is a number that is only divisible by 1 in itself, and we'll be talking about n-bit primes. So by that I mean a prime from 2 to the n minus 1 to 2 to the n minus 1. And if the prime is larger than 2, that means its representation in binary is of this form. Okay, so I have 1s at extremes and 0s and 1s. So that's an n-bit prime. And there are two fundamental questions you can ask about primes from a computational perspective. So one of them is, if I give you an n-bit integer, can you test if it's prime? And this problem has been solved by the AKS algorithm, so it can compute if a number is prime deterministically in polynomial time. And perhaps a second very basic question is, how do you generate a large prime, an n-bit prime? Okay, and this is the focus of this talk. Okay, so more formally, here's the challenge. You give an n, and your task is to construct a fixed n-bit prime. And we would like to solve this problem deterministically in polynomial time. Okay, so this would be the ideal result. So let me tell you now about a few different approaches one can try to solve this problem. So the first, most naive algorithm is the following. So you give an n, so you just try all integers one by one, starting from the first n-bit integer. Okay, so you test each one using, say, the AKS algorithm, and if that integer is prime, then you output. That's your output. Okay, so that's an algorithm that would definitely produce an n-bit prime. And if we could understand gaps between different primes, then we would be able to place an upper bound on its running time. So there is an old conjecture called Cramer's conjecture that says if you look at the k prime, then the gap between this prime and the next one is log square. Okay. So if this conjecture holds, then we know that this algorithm is going to inspect at most n square numbers. Okay, and therefore it runs in deterministic polynomial time.
Well, this is because you write big O, not
yeah, so we look at primes of magnitude roughly 2 to the n, so this would be like n squared, yes. Okay, but unfortunately the state of the art is much worse than the conjecture. So it's a polynomial in P, so this only gives exponential time algorithm. Okay, so this simple approach, if, at the moment we can only prove it runs in exponential time. Now the state of the art for generating primes in deterministic time is obtained from an algorithm given in the 80s. So this is the idea. So first you design a procedure that can approximately count the number of primes in a given interval. And let's say if you have an interval like this contained here, then it can tell you approximately the number of primes in time 2 to the n over 2. Okay? So once you have this procedure, you do a binary search. You estimate the number of primes on both sides of the interval, and you recurse on the side where your estimate is larger. Okay? And you can keep doing this until you reach an interval of size just 2 to the n over 2, where you can just brute force now all the integers there until you find the prime. Okay, so that's the best known deterministic algorithm that generates an n-bit prime. Now, let's look at an easier question. Now, I only require you to generate infinitely many primes. Okay? And here's a simple procedure that tries to solve this question. So given n, we just output a sequence of n ones. Okay, so that's the algorithm. And if we had a result saying that there are infinitely many primes of the form 2 to the n minus 1, then these primes, if you write them in binary, they are just sequence of ones. And then this will be an algorithm that succeeds infinitely often. Okay? So that's the simplest possible algorithm you could have. But again, unfortunately, we don't know if this conjecture is true. Okay? So this only gives a conditional algorithm. Okay, so let's now look at a slightly more general class of problems, and then I'll be able to tell you about a different approach to construct primes. So let's say that a appropriate queue of strings is dense if on every input length n, we have at least 2 to the n over poly n strings satisfying Q. Okay, so that's going to be a dense property for us. And we know by the prime number theorem that the set of primes is dense. And now we can ask this general question. So if I give you a dense property Q, can you find an yes instance of Q in polynomial time? Okay, so this is a generalization of the problem of generating primes. We call this the explicit construction problem for Q. We're going to assume it later, but for now, that's just the definition of the problem. Okay, I'll give you a dense property, can you generate a yes instance? And if you could test whether Q is easy, like Valentin was asking, if you can easily test when something satisfies Q or not, then now you can use the following simple procedure to generate an object satisfying Q. You sample a random n-bit string until you get one that is in Q. Okay? And by the density of Q, we know this procedure will take a polynomial time. Okay? The expected running time is polynomial. So this is very easy to do with randomness, but ideally we would like to have a deterministic procedure. Okay. Okay, so how we might be able to get a deterministic algorithm? So one approach is to use pseudorandom generators, okay, like Valentin introduced in his talk. So pseudorandom generator is a procedure that constructs a subset of strings that has pseudorandom properties. Okay, so in the case of trying to generate a prime, we know that a random n-bit string is going to be prime with decent probability. If we had a set of strings that behave like a truly uniform random string, then we should also be able to find a prime inside the set. Okay, but the advantage is now that the set might be much smaller and it might be easier to just enumerate the elements in the set. Okay, so if we had such a pseudorandom set, again, we could just now enumerate everything there and check if one is prime. But of course, the difficulty is how do we construct a pseudorandom set with the properties we need? And using techniques from complexity, we can construct such a set, but at the moment only under very strong computational assumptions. Okay? So for instance, if E requires exponential size circuits, then we know that this set GIW has the pseudorandom properties we need so that it contains a prime. Okay, so that's another conditional construction. But we are very far from establishing this conjecture. Okay, so the best no lower bounds are only linear. So again, we can have a conditional procedure, but obtaining an unconditional result seems very difficult. Yes?
In principle, right, since you are just trying to solve this particular problem, in principle, you could have some kind of weaker tester for the sequence, specifically some kind of number theoretic.
Yeah, so Peter's comment is we don't need to fool a very complicated class of tests. We only need to fool the test that checks if an input is prime. And indeed, we're going to explore this later in the talk. Okay, we're going to be looking at a more restricted class of tests. So we don't need a pseudorandom generator that is as generous as this one to solve the problem. Yes. Okay, so here's a brief summary. So we have some constructions, and they succeed in running polytime, but we need to make assumptions. Some of them about number theory, some of them about complexity. But the state of the art for unconditional results remains 2 to the n over 2. Okay, so So that's our challenge. Can we find n bit prime in polynomial time provably? So that's what we would like to do. And this is a very fundamental question. So it was the topic of a polymath project many years ago, where they mostly explored number theoretic techniques trying to make progress, but unfortunately, no unconditional improvement was obtained at the time. Okay. So yeah, this remains a very difficult question to do it deterministically and in less than 2 to the n over 2 time. So for this reason, we're going to relax our goal, and we're going to be looking at what is called pseudodeterministic algorithms. So to introduce this, let's just review again the randomized procedure, where now you have this dense property. We keep sampling random elements until we find one that satisfies Q. So that's a great procedure. It does produce a prime. But it comes with an issue, which is if you run this algorithm twice, we won't get the same prime. Okay? And ideally, we would like to have a canonical prime that is produced by the algorithm. So in other words, for the randomized algorithm, if we look at its computation paths based on the random input, then we might generate very different primes on different executions, and sometimes we might even fail if we are unlucky. On the other hand, the ideal scenario is we would like to get a deterministic procedure, just gets n and outputs an n-bit prime. Okay? So we're going to compromise, and we're going to consider what is called pseudodeterministic algorithm. So this is still a randomized procedure, but on most choices of the random string, it generates a canonical output. So in this case here, this will be like a canonical prime that is produced by the algorithm. Okay? So the pseudodeterministic procedure is randomized, but it outputs the same answer with high probability. And if you were only looking at this algorithm as a black box, and someone is running it multiple times, for all practical purposes, the impression that you would have is that it's a deterministic procedure, okay? Because it would generate the same output. Questions about this definition? Okay. So this notion was introduced by Ehrengarten, Schaffi, Goldwasser in 2011. And since then, it has been investigated in many different contexts. Query complexity learning, computational algebra, and so on. But the main question they asked in that paper is, can we generate n-bit primes pseudo-deterministically in polynomial time? Okay.
But can you just give some example
Yeah.
of this pseudo-deterministic algorithm, which is not deterministic?
Yeah, I'm going to give you one example in the talk.
Yeah.
Okay. But yeah, there are many algorithms that have been designed. Yeah, for instance, you want to find some bipartite matching in a graph and very efficient parallel time. So can you do this pseudo-deterministically so that you all produce the same matching with high probability? So that's an example of...
And you can do that.
Yeah, you can do it pseudo-deterministically. But there are some related questions that, like, can you do it deterministically in very fast parallel time? Some of these questions are still open. Yeah, so, but yeah, there are many papers on this topic at the moment. Okay, so not just primes, you could ask more generally, like if you have this dense property that is easy to decide, can you generate yes instances in pseudo-deterministic polytime? Okay, and we'll be interested in this question. Okay, so before, I'm going to present a result from last year, but the most relevant previous result was this one obtained in 2017, where we proved the existence of a sub-exponential time procedure that, given n, will generate a canonical n-bit prime with high probability, and it succeeds on infinitely many input lengths. Okay? So it's a sub-exponential time algorithm. It generates a canonical prime with the caveat that it won't succeed on all input lengths, but only on infinitely many of them.
But it's deterministic or pseudo-deterministic?
This is pseudo-deterministic, yes. So it generates this fixed prime with exponentially close to 1 probability. Okay. Yes?
So, you show us a polynomial time.
Yeah, yes.
But the density of
ends will be better or worse than this?
Yeah, the gap between the good input lengths is better in this result. It's polynomial. And in the one that I will present today, which is the polynomial time algorithm, the gap can be exponential. Yeah. More questions? Okay, so that's the improvement from last year. Joint work with Li Jichen, Zheng Jianlu, Hanling Ren, and Rahul Santana. So now we have a polynomial time procedure that generates a canonical prime with high probability, and it succeeds on infinitely many input lengths.
Was the previous one also infinitely many?
Yes, yeah. So it's the same result, except that the running time goes from sub-exponential to polynomial. Yeah.
But it's not a strict improvement because it's that's about
Yes.
it's sparse.
Yes, if you look at the gap between the good input lengths, it's not an improvement. Yes. Okay, so I'd like to sketch the proof of this result. But before, let me tell you about the consequence in Kolmogorov complexity. Okay. So the following result follows from that theorem, that there are infinitely many primes with succinct and efficient descriptions. So what do I mean by this? So for every m, we can find n larger than m, and some n-bit prime p, such that the RK polycomplex of p is at most roughly log n. Okay? And recall that the RK complex of a string is the minimum length of a randomized program that generates the string with high probability. Okay? So that means we have large primes that we can easily recover from just roughly log n bits of information. And in
Given n, it's order 1, right?
given n is going to be of order 1, yes. Okay, so this follows immediately from the previous theorem. So we have this fixed algorithm, this object of constant size. And if we fix a good input length n, then it generates some canonical prime. And therefore, the algorithm together with n, they serve as an encoding for this prime. Okay. Any questions about this result? Yeah, and here I'm stating an immediate consequence of the theorem, but if you work harder, you look at our algorithm and you can try to have some control over the inputs and so on, you can actually prove an upper bound of log n. But I'm not going to discuss it today. Okay, so now let me discuss the more general form of the theorem. So it turns out that the only properties of primes that we use in this proof is that they are dense, and it's easy to decide if a given integer is prime. And the most general result that we have in this work is that we can have the same algorithm with similar properties for any dense and easy property Q. Okay? So formally, so you fix this property Q, and it's dense enough and it's easy to decide, then we can generate strings satisfying Q infinitely often in pseudo-deterministic polynomial time. Okay? So for every Q, you have a different algorithm that will generate the string in Q. And this previous paper from 2017 and it also works in this general setting. It only needs to use the fact that Q is easy and dense.
It uses the algorithm for Q as a black box. Or not?
The polynomial time result won't use it as a black box. Yeah.
And if Q is in BPP, it's not enough.
If Q is in BPP, then the result from 2017 would still work. The one with polynomial time doesn't work. Yeah. Yeah, so there is this very interesting property of the proof, which is we actually need to use the code of an algorithm deciding Q to produce the canonical inputs satisfying the property. So it's not a black box proof. Yeah. And the previous result from 2017 used it in a black box way. You could have like a oblivious construction or like some kind of pseudo-random, pseudo-deterministic pseudo-random generator that would work for all Qs. What do you mean?
What you get from Kashmir-Wigderson generator would also be black box.
Yes, exactly, yes. Yeah. Okay, more questions about the results? So. Okay, if you're not, now I would like to sketch the proof of the polynomial time algorithm. And it builds on the previous construction. So let's first do the sub-exponential time regime. So that's what we would like to show, that there is an algorithm running in 2 to the n to the epsilon time, and it generates an n-bit prime with high probability, and it works on infinitely many input lengths, okay? And this proof uses 2 key ideas. We're going to explore the hardness versus randomness paradigm, and we're going to use a non-constructive win-win argument in the proof. Okay, so let's review some of the basic ideas from pseudo-randomness introduced by Valentin. Okay, so we'll be interested in constructions of pseudo-random generators. So remember, this is a procedure, G, that maps a short seed into a longer string that has pseudo-random properties, okay? And in these constructions, G will depend on some hard function or language, okay? So the generator is built on top of some function or language L. And as part of the proof of most of these generators, it would establish the following result. If L is a hard problem in some sense, then the generator is pseudo-random against some class of tests. So from hardness, you get pseudo-randomness. And the way you establish these results is via a reduction, okay? So you would assume that there is a test that breaks the generator, and then associated with this generator, there is an efficient reconstruction procedure that uses the test and computes the language, okay? So it's a constructive proof, and therefore, if the language is hard, then you shouldn't have such a D that distinguishes the output of the pseudo-random generator from random. Okay? But as in Valentin's talk, we use this both in this play-to-win and in play-to-lose situations. Okay? And we don't actually really know in which one we are. The important point is we have this reconstruction procedure. And in its most basic form, this is one of the classical results, you can get a generator that is non-uniform. So what does it mean? It means you make a very strong hardness assumption about the language, that it's hard against non-uniform computations, and you can fool non-uniform tests. Okay? And the reason you have this in this generator is because the reconstruction procedure itself requires a device. So it will work in a setting where a device is not expensive, okay? But in our applications, what we would like to do is to generate primes. So we're trying to fool a uniform test, let's say the AKS algorithm. So we won't need such a powerful generator. We only need to fool uniform tests. So for that, we can rely on the uniform hardness versus randomness paradigm, which is an extension of this result. But it has a restriction. So in this theorem, you could start with any hard language, and you get pseudo-randomness. Now, in this case, where we are in the uniform world, to establish this connection, you need the language to have some additional special properties. Okay? So these properties won't be important in our discussion, but this connection won't work for every language. Okay? So if this language is special, then now given any distinguisher for the generator, we can compute the language using the reconstruction, and this provides a uniform reconstruction. Okay? So it works on every input length, and what you get at the end of the day is a uniform algorithm, a Turing machine. Okay? Turns out that this was going to be a randomized Turing machine, so that's why I have this dice here. But it's still a uniform procedure. Okay. Okay, and we're going to rely on a language with these properties that is p-space complete. Okay, this was introduced by Trevisan Vadin, and it's sufficient for us in the application. Okay, so how can we use this uniform pseudorandom generator construction? So what we care about is the set of primes. Okay, so we instantiate the generator with this special language from Trevisan Vadin, and we would like to understand whether we fool or not this test, the set of primes. And what we get is that in case this generator doesn't fool the test, then the reconstruction procedure, given this distinguisher, the test for primes, can compute LTV, okay, a p-space complete language. So that's how we're going to use this result. So we'll try to use the generator with the set of primes, and if it doesn't work, we can compute the original p-space complete problem. Okay? So let's see how this is done in more detail. So here is the AKS algorithm. So it's a polynomial time deterministic procedure. We'll be looking at it with input length m. And we know it accepts 1/m fraction of inputs, okay, by the prime number theorem. So now we would like to instantiate this generator using this LTV language and stretch the input from n bits to m bits with the hope that it's going to produce some prime. Okay, and you can think of m as being a large enough polynomial. Okay, so m is like, if the seed is n, m is like n to the c. Okay, and actually all we need if we want to generate a prime is something weaker called the hitting set generator, because we only want to produce one prime. We don't want to approximate the probabilities of the test or anything like that. Okay, so we want to hit this set of strings, this set of primes. So all we need is a hitting set generator. Okay, so that's the framework. And now what we discussed before is that in case this generator doesn't fool or doesn't hit AKS, then we know we can use the reconstruction algorithm with AKS as the oracle to recompute the language on n-bit strings. Okay, so that's the setup. And now the question is this generator going to hit the set of primes or not? Okay. And because we don't know, we're going to consider the two cases. Okay. So one is when the generator doesn't hit an m-bit prime. And in this case, this language can be computed efficiently using the reconstruction procedure. And in the other case, well, we have a prime, right? So we now need to compute what's the running time of this procedure. So yeah, let's try to do it more carefully now. This is precisely what we call win-win argument. So we consider both cases and we show that in both of them, something good happens for us. Let's call this case hit. That's when the output of the hitting set overlaps with the set of primes, with the AKS test. So in this case, we have a good hitting set generator. So we can enumerate all the seeds, and we check the first string that is a prime, okay, that is accepted by the AKS test. And because we're stretching the generator with a polynomial factor, we're running into the n time, but we are producing an m-bit prime for a large polynomial. Okay, so that's like a sub-exponential time running time with respect to m. Okay, so that's a great scenario. We have a sub-exponential time procedure generating this m-bit prime, and we are happy in this case. Okay. So any questions about this case? So this is a typical way of using this generator as we go through all seeds and using the guarantee that one of the seeds leads to a yes input. And because we can test the yes inputs, we're going to be able to find a prime.
That's the infinite open case, no?
That is the, okay. I didn't want to get into this technical discussion. Yeah, let's say this is the infinitely often case. Okay. Okay, now the second case is when we are unlucky, and this is not a good generator. Therefore, this hitting set does not hit the AKS test. But thanks to the reconstruction procedure, now we can compute the hard LTV language in polynomial in m time, which turns out to be just polynomial in n, due to our choice of parameters. Okay, so we have this polynomial time algorithm for a p-space complete language, and now we're going to use it to find the prime. So because this is complete for linear space, we can just, in linear space, enumerate our strings, test the first one that is a prime. And because we can do any such computation now in randomized polytime, we can also find the lexicographic first prime in randomized polynomial time. Okay? And that's the pseudodeterministic case, because we are simulating this p-space computation with randomized procedures, but we succeed with high probability. So we output the lexicographic first prime with high probability.
But I thought you wanted an n-bit prime.
Yeah, so thanks for, exactly. So what is happening here is we are considering two input lengths at the same time. One is m, which is n to the c, and one is just n. And what this argument is showing is that in one of them we're going to succeed. So I'm going to get back to this in the next slide, I believe. But that's all we want, right? We want to succeed infinitely often. So yeah, that's a very good point. More questions about this construction? Okay, so here's a summary again of what we have just done, and that's connected to Bruno's question. So we look at two input lengths, n and n to the c, and we analyze two possible cases, the hit case and the avoid case. So to do that, we fix this p-space complete language. We instantiated the hitting set generator with polynomial stretch. And in the case hit, this is a good hitting set generator. And we can find an n-bit prime in time 2 to the n. In the other case, which is the avoid case, now the hard language can be computed in polynomial time. And we can use this hard language that is p-space complete to find an n-bit prime. Okay, so we are now on this input length here. Okay, so how can we move now from sub-exponential to polynomial, which is our goal?
So if I understand the
Yeah.
algorithm, on every length runs both.
Let's say you partition the integers into blocks, and inside each block, you consider these two input lengths inside the block. And you know that in one of them you're going to succeed. You don't know which one. So when you are at this input length, you try to use the hitting set. When you are in this input length, you try to use the reconstruction procedure.
But
Yeah.
I can always, at every input, I just take
Yeah.
an algorithm which at every input length runs both. And I'm not guaranteeing that at every input length this will work. But, right, so if I'm on an input length where here it doesn't work,
Yes.
then neither the hit algorithm nor the avoid algorithm worked. That means that further back and further
Yeah.
ahead it must have worked.
Yeah, you could try to extend the approach in this way. But since you won't leave the infinitely often regime in any case, then...
But I want the same algorithm for every length, right?
Okay, so you have a fixed algorithm, okay? In this case, you run the hitting set generator in 2 to the n time. And in this case, you run the reconstruction procedure.
Oh, you're saying that one of them must happen infinitely often.
One of them is good infinitely often.
Okay, got it.
For every pair of inputs like this, one of them will succeed. Okay, so you just make several pairs, and then, yeah. More questions? Okay, so now we want to do it in polynomial time. And one observation here is that there is one case in this analysis where you already get polynomial time. And this is in the case of the avoid case, because now the reconstruction procedure runs in polynomial time, and therefore we are in good shape in this case. However, the hit case is too slow, right? It runs in sub-exponential time only. And the idea is that although it's slow, we are making some progress in the hit case, okay? And the progress is that first, when we didn't have anything, we had to brute force over all n-bit strings. But at least now, in the hit case, if you look at the set of n-bit strings, and this is the strings in the output of the hitting set generator, you know that there is some prime here, okay? And this hitting set is of size 2 to the m to the epsilon. Somehow we started from like just doing a trivial brute force search, and now the bad case in the analysis, we gain something. We now know there is a prime in a set that we can compute, and this set is of sub-exponential size. So what we would like to do now is to iterate this idea, maybe by using additional input lengths, so that we keep making progress, okay? So that's what we would like to do.
Can you explain again?
Yeah, so there are two cases. In one of them, it already runs in polytime, which is great. The second case runs in sub-exponential time.
But why sub-exponential? The hits?
You could play with the parameters and then you get a half exponential upper bound. In one case you have polytime, in the other case you have sub-exponential time. You can improve the analysis and get something called half exponential time upper bounds.
So it comes from Impagliacci, I think that's one that's...
It comes from this wing-wing analysis, and if you set the parameters then so that both cases match the running time, then you get something called half exponential. Yes.
But the idea is now is that you now looking apply the same procedure, but not for the same set of primes, but for the set of seeds that generate primes.
Yeah. So now you would like to sort of apply the same approach, but instead of sort of like in the p-space case, we had to brute force over all primes and find the lexicographic first. If you could, in that case, now brute force over the strings in the hitting set, then that takes less time. Okay, you'd like sort of now try to repeat this. That's sort of the intuition for what's going to come next.
For searching inside this heat space,
Yeah.
you search just inside of a pre-image in the seeds.
Yes. So when I say H here, I mean the set of output strings generated by all the seeds.
Yeah.
Yes. Yeah. Okay, that's the intuition. We would like to implement this idea somehow. Okay. And to be able to do that, we're going to rely on recent technology. So this is a new construction of a hitting set generator done by Chen and Tell. And its advantage is that before, we had to apply this hardness versus randomness paradigm with this special language L, this LTV language. But now we have a hitting set that we can apply to any function f with some conditions. But these are like more general for us. So let me tell you about this hitting set generator. So fix now any uniform function f that takes 1 to the n and produces an n-bit string. Okay? And assume this function can be computed by a uniform sequence of circuits of depth d and width t. Okay? So here's a picture of this Boolean circuit. So it has d layers, but it can have inside each layer up to t gates. Okay? So maybe let me give an example of a circuit like this, because it's going to be useful. So consider the circuit that tries to output the lexicographic first n-bit prime. So how can we implement this? Okay, so we have this 1 to the n, that's the input to the circuit, and we want to find the lexicographic first n-bit prime. So we can run in parallel the AKS algorithm on all n-bit strings. And after that, we can pick the lexicographic first. Okay? So we can now do a binary tree here where we always take the lexicographic first of the strings until we output the first n-bit prime. Okay, and what's now the depth and the width of this circuit? So that's the question. Okay, so the depth of the circuit is the depth of the AKS procedure, which is poly n, and log of the size of this tree, which is again poly n, right? So the depth here is poly n.
You don't have to use AKS, right? Just
Let's say you could do something else. Yeah.
then the depth would be like order n.
Yeah. But poly n and n won't make a big difference for us. Okay, so that's the depth and the width. Because we're running all these AKS subcircuits in parallel, then the width is going to be roughly 2 to the n, right? Okay, so that's an example of a uniform function f, like this, with these parameters for depth and width. Now the Chantal generator says the following. So we can pick any m between log t and t. So we have some m here. And we can construct a heating set generator, H, mapping log t to m. So this m has this constraint, so from t, log t and t. And the running time is polynomial in t. And it has the following property. So that's just a picture. So we're stretching log t bits to m bits. And we're using f in the construction of the generator. And the most important property is the following. So if this construction doesn't hit some test d, so if some test d avoids the generator, then we can use its reconstruction procedure to compute the value of f from 1 to the n in time poly d capital M. Okay, so the reconstruction Rd runs in time okay, so the important thing to notice is that we don't have a dependence on t in this running time, only on the depth and on the stretch. Okay, so in particular, if we can have a test that avoids a generator based on this brute force procedure, because its depth is poly n for this function f, if the stretch is, let's say, also some large polynomial, then the reconstruction procedure runs in polynomial time. And in this particular example, this function f is finding the lexicographic first prime. So if we can reconstruct its output, we're actually computing an n-bit prime. Okay, so that's the Chantal generator. It works for any f, which is a uniform sequence of circuits. There is a technical condition, it has to be log space uniform, but I'm not going to discuss it further in this talk. Okay, so you have a sequence of circuits, you build a hidden set. If it doesn't hit a test, you can reconstruct the computation of the function in time polynomial in the depth without dependence on the width. Okay, that's where we have our savings. Questions about this result? We're going to now go back to the approach in the sub-exponential time using this more general technique. Okay. Yes?
So the how fast does the circuit compute the function?
The heating set or the circuit?
The function.
Okay, so the function f admits a sequence of circuits of width t and depth d. And the circuits have to be log space uniform. Yeah. Okay, so let's use this generator now. Okay, as before, we're going to fix m, so we're going to have a polynomial stretch. And we will consider it as our first function, this brute force circuit that I just described. So let's call it BF0. So it enumerates our strings and takes the first prime. So that's BF0. And we instantiate the chain-tail generator with this f as the hard function. And it will stretch log t bits, which for us is linear in n, to capital M, which we're going to choose to be poly n. Okay, so we have polynomial stretch. And we also have this reconstruction procedure. Okay, so we will try to use the generator with the AKS test. And if it doesn't work, then we will reconstruct using AKS. Okay, let's do the two cases again. So let's recover the original result using this generator. So in the first case, if AKS avoids the generator, then now we can reconstruct the function in time polynomial in D and M, which for us is poly n. Okay? So in the avoid case, we again obtain a prime in time poly n. And in the no case, we are at a similar situation. We have a hitting set, it hits AKS, so there's at least one prime there, and we can compute in 2 to the n time. Okay, so this is precisely this situation we had before, except that now we have a more general hitting set. We can use any function f with some properties on it. And that's what will allow us to recurse in this case. Okay.
Is the point that there the width was 2 to the n, but now you've shrunk the number of strings to be the outcome of a hitting set generator? So you replace the 0 to the n, you replace all the strings with the first output of the hitting set generator, the second output, and I've shrunk the width because the seed was small.
Yeah, so next time we're going to use this, this t is going to decrease relative to the new input length, and we're going to make progress. Yeah, good point. Okay, so we're going to iterate the idea now. So we're going to be looking at more than 2 input lengths. So the next input length is some polynomial in the previous input length with exponent beta. So we consider initially the trivial brute force procedure that takes 2 to the n time. So maybe just keep track of it here. So that's the first input length. We sort of have a trivial hitting set. You can think of it in this way. So we have this algorithm, and the hitting set h n0 is just all strings of length n0. Okay. And we build this hitting set generator as we discussed before. And we consider 2 cases. That's what we did. In the avoid case, that's great. We have polynomial time reconstruction. But in the hit case, something very useful happened for us. So now when we look at the next input length, n1, and we consider the output of the new hitting set generator. Okay, so that's what we did, right? So we took this function f, we construct a hitting set generator for a larger input length n1, n0 to the beta. So that was our m before. Okay, and now we know that there is at least one prime here. Okay, so that's the hit case, and we're going to try to recurse now on this case. So to recurse, the new brute force procedure is only going to search for a prime inside this set. Okay, so it will enumerate all the strings. So it relies on this hitting set. So you enumerate all the strings here, check each one if it's prime or not, and outputs the first one. Okay, so that's the new BFN1 brute force procedure. And by the properties of this Chantal generator, the running time of this procedure is poly in T. And T for us is the size of this set here. Some T1. Okay. So before the size or the complexity of the generator was T0 was 2 to the N0. The complexity of the new generator is T1, which is, we had the seed of length log of T0, so, and then we enumerate. Now we're going to use T1, we enumerate. So every time we do this, we only pay logarithmic in the seed length. Okay. Okay, so here are the details. We are in this case where there is a smaller set. We're searching for a prime inside the set. The complexity of generating the set is T1, is some polynomial in T0. And the seed length is log of T1. Okay? Because the complexity of the hitting set is the running time of the function BF. Okay? So if your function BF is searching in a smaller space, then your new complexity of the next hitting set is polynomial in the size of that space. Okay, and we consider again two cases. Whether the next generator on input length N2, so we use this BF1 and generate HN2, and we also define new brute force search procedure here. And we just recurse again, okay? If it avoids, then we can compute the function f in the previous generator, which was searching over the smaller space. If it doesn't avoid, we have a new hitting set hitting a prime on the next input length. And I'm going to discuss in more detail next, but the progress we're making here is that relative to the new input length, the size of the current hitting set is shrinking. Okay, so this sub-exponential gain we had in the first stage, we will keep getting it in every stage of the proof. Okay.
So beta is going to be what?
Say again?
Beta.
Oh, beta is going to be some large enough constant that is larger than the overhead of the hitting set. And I'm going to get back to this soon. Okay, so we iterate, we have a new brute force procedure for the next hitting set, and so on. Okay, and eventually we'll have to stop. Okay, and we're going to discuss this soon. But that's the idea. So to keep iterating, now that we have a hitting set construction that works for any uniform function f, we look at the time taken to compute f. That's going to be essentially the size of the previous hitting set. And the complexity of the next hitting set is just poly of that complexity. So it's kind of like controlled. But then we stretch a little bit more every time, so we have some gain. Okay, so that's the intuition. So let's have a closer look now at these parameters. So Ni is the length of the prime you want to find, okay, in the ith iteration. So we start with input length N0, N1, up to Ni. So Hi is going to be the hitting set generator that supposedly contains a prime for the ith input length. Okay, think of this as Hni. This is Ni. And Ti is always the size of Hi. So that's how we define Ti. And it's essentially the complexity of doing the brute force search. Okay, once we have generated all the elements, we just check one by one. So Ti is the size of roughly the complexity of computing the entire set of this generator. And initially, in the base case, T0 was just the brute force hitting set, was 2 to the N0. In the formalizing the ith case, we define this BFI procedure. So it enumerates all the strings in the ith hitting set, output the first prime, if it finds a prime. The next hitting set uses this brute force search as the function f, and so on. Okay. And the key measure of progress here is how the input lengths and the size of the hitting sets are increasing. Okay? So the input length grows by some beta that we pick at the beginning of the proof. So that's the stretch we are doing at each stage of the iteration. Okay? And the running time or the complexity of producing the hitting sets increases with an alpha exponent. Okay, so that's a fixed constant that only depends on the Chantel construction. Okay, so if your initial function f runs in some time t, then this generator will have seed length log t and runs in time poly t. So it's some fixed overhead that we have. Okay, so now, and finally, we did this two-case analysis, whether we hit the prime in the ith case or we avoid the prime. Okay, so what are we hoping to get? So how are we making progress here towards a polynomial time procedure? So what's happening is that the TI, so the complexity of producing TI is increasing in absolute terms, like how many steps of computation I need to generate the set TI. But relative to the input lengths, it's not increasing, okay? It's decreasing. So we're stretching a little bit more than the overhead from the running time. And the hope is that if we do this enough times, then eventually the input length is large enough so that the size of the hitting set is just polynomial in the input length. And therefore we can just enumerate and have a polynomial time algorithm. Okay, so that's the hope. Okay, so we need to understand these two parameters, Ni and Ti. And we are able to set beta large enough so that these Ni's, they grow faster than Ti. So we are free to pick beta, which is going to be the stretch of the generator in each application. Okay, so this is what happens. So at every stage, we increase the exponent by beta in the input lengths. And also in every stage, there is an overhead in the size of the hitting sets, which is raised to alpha. So at the ith iteration, we have length n0 to the beta I, and ti, we start from t0, which is just the exponential case. We get some alpha to the I. And we want to find the smallest t so that after t iterations, the size of the hitting set is polynomial in the input length. Okay? So what we do is we set beta to be 2 alpha so that the input lengths, they grow reasonably faster than the running time overheads. And if you do the math, then after just log n0 iterations, we're going to have that the size of the hitting set is polynomial in the input length. Okay. Any questions so far? So I'm just saying that after enough steps, what's going to happen is that the size of the hitting set is polynomial in the input length. Okay. And if you set beta 2 times alpha, then this happens with log n iterations. So any questions so far about this argument? Yeah.
Here you use something except for the density and polynomial decision algorithm.
So far I haven't talked about the correctness. So I'm just doing a construction where in different input lengths I iterate a previous hitting set, a brute force search, and so on. And I'm saying with this choice of parameters, after log iterations, t and n become very close. Okay? And I'm going to talk about correctness now and give you like a pseudocode for the procedure. Any additional questions?
So this gives us exponential stretch of the input length.
Yeah, so right. So we're going to have log n0 iterations starting from n0. And because we're growing polynomial at each step, you might end up with a final nt after these t iterations, which is roughly 2 to the n0. So, and we'll prove now that it succeeds in one of these stages, but we won't know in which one. More comments or questions? Okay, so here's the final procedure. So first thing we do is we partition the inputs, the input lengths, into blocks. So we have some n0, some n1, some nt. And this will be repeated again with a different n0, and so on. And what we're going to show is that in each one of these buckets, there's going to be one good input length. Okay? So now your algorithm is giving some value 1 to the n. It checks if it's one of these special input lengths. If it's not, then it gives up. If it's one of the t input lengths, then it will compute in the following way. So if I equals t, so that's the last input length after log n stages, then it will hope for the best. Okay, it will say, well, maybe the final Hitten set of polynomial size does contain a prime, so I'm just going to iterate over the elements, and if there's a prime there, that's my output. So that's the code of the algorithm in this case. And if not, if it's in one of these intermediate input lengths, it also just hopes for the best that the Hitten set here is avoided by the next input length and that the reconstruction procedure is correct. Okay. So that's the algorithm. Note that it always runs in poly time. So the extreme case NT, there is a poly-size Hitten set. The intermediate case, the reconstruction is always poly time.
So if you have a hit case before E, that's not a problem?
If you have a hit case where? Mm-hmm.
So during those iterations, if you win with a hit
Mm-hmm.
before T, you're also going to reach this?
Yeah, so let me explain now why it always succeeds. Yeah. Okay, so let's first look at the case where the final Hitten set contains a prime. Then in the final input length, we find this prime. Okay. Now, if the final Hitten set doesn't contain a prime, because the initial Hitten set does contain a prime, it's the set of all strings of length n0, then there must be some stage I where hi contains a prime, but the next Hitten set does not contain a prime. Okay? And for this I, the reconstruction procedure will succeed. Okay? So you started with a good Hitten set, you ended up with a bad Hitten set. At some point, there's a transition from good to bad. And in that point, the reconstruction procedure succeeds. Okay? So when it succeeds, it computes the previous brute force search. But you're doing the brute force search over a Hitten set that contains a prime. Okay? And that establishes the correctness of the procedure. Does it answer your question? More questions about the algorithm and its proof of correctness? Okay, and just to be clear, so now you want this algorithm to succeed infinitely often on infinitely many input lengths. So what you do is you partition the integers into like blocks. So let's say n0 is just 2. And then you define all these values up to nt. And then you pick your next n0 larger than the previous nt. And you do again another block of inputs and so on. And this procedure is guaranteed to succeed on at least one input length inside each one of these blocks. Okay. Okay, so this exposition, I had to omit some technical details. I briefly mentioned that this Chantal generator doesn't work with all functions f. It needs to be a uniform, log space uniform computation. Fortunately, it's possible to verify that these brute force procedures, they are uniform enough. So they are reasonably simple procedures, and the uniformity is not hard to establish or not too hard. So that's good. The original generator didn't have the optimal stretch that we needed to get polynomial times. It would only give you quasi-polynomial time. So to actually get these parameters, we had to improve a little bit on the seed length complexity of the generator. And to do that, we had to replace some components of the Chantal with something called the Choutiao humans PRG. But yeah, I won't be discussing these extensions. Okay, so open problems. The main challenge is still to be able to generate a prime on every input length This would be very interesting, or at least to reduce the gap from 2 to the n to something better. We have improved the running time compared to OS 17, but it has some nice features that this algorithm doesn't have. So one of them is that it achieves 0 error. So the sub-exponential time algorithm either outputs the canonical prime or some like error symbol on a given input length. While this proof here, we don't get the 0 error property. So this reconstruction procedure of Chantel might give you a different prime or something else in some cases. Okay, so it's not 0 error. It would be nice to have this as well. As I mentioned before, OS 17 works for properties in BPP. This procedure really needs the property to be in P. So we are making use of the AKS primality test. Okay. And there's something curious about it, which I briefly mentioned, which is the actual code of the algorithm deciding Q, let's say the actual implementation of AKS, it will affect which canonical prime you get using this construction. So it's a non-black box construction. And this is thanks to the Chantel generator, how it's constructed using Q. Okay, so the main reference is this paper from last year, and thank you.